Okay, welcome back. We're looking today at trig identities, getting started at least on trig identities. There's a lot to learn here, or a lot to do here. The basic idea is that we're working these out as if they're little puzzles. Each one's going to be different than the next, and so learning a series of things to look for is the best we can do. There isn't going to be a right way to solve any of these, or any of the questions you see this year. What will happen is one solution will be as good as the next. One might be shorter, one might be fancier, but basically, if we get to the end result that we're looking for, then they will always be okay. So just some key concepts here to get started. These are straight from the textbook. Trig identity is an equation with trig expressions on each side that are true for all angles. One way to show that an equation is not an identity is to determine a counterexample. Okay, something that we probably won't do a lot of, but just the basic idea that if you're trying to prove something is true, if ever you can find even one example where it's not true, then overall the proof is not true. The equation is not true. So sort of, for something to be true, it has to be true for every single possible value. As soon as there's one value for which it's not true, overall, the identity or an equation of any sort would not be true. To prove that an equation is an identity, work with each side of the equation independently. Okay, so this comes down to what we've done a few times now with left side and right side. We have to work with them this way. When something says prove these are true, we don't know they're true until we're done the question. So we can't actually write that this equals this at any point in time in the question until we're absolutely positive at the very end that in fact they are equal. The basic trig identities are the Pythagorean identity, quotient identity. I'll have these on the next page. And again, they're on page 237, I believe, of the textbook. And trig identities can be used to simplify solutions to problems. That's just sort of an understanding of why a little bit. Okay, so some of the keys here, off to the right, these are the identities that we can start with. These are established. Things like tan being sine over cos. The reciprocal identities by definition, the compound angle formulas that we saw already, and the Pythagorean identity you may have seen written down once or twice in the notes or in the homework. Basically, that's a starting point for us. We can always assume that to be true, not assume that to be true. We can always know that to be true and can make use of it if it helps. And so a list of possible hints or tips to look for. As always, we have to separate the expression separate the identity or the equation into two separate expressions and work with them independently. Good idea to always start with the more complicated side. You can always switch to the other side if you get to the point where the one side's looking pretty simplified and you can't do much more with it. Always express everything in terms of sine and cos, essentially. And if you get to the point where you have sine and cos on both sides, but they're still not looking very similar, establishing a common denominator, if you have rational functions, will get you a lot closer to where you want to be. We can always factor and then cancel, of course, if that's something that's a possibility. And I sort of said before, if you get stuck on the one side, you can switch. Usually, with the Pythagorean identity, we want to go the other direction. We usually want to change a sine squared plus a cos squared to be 1, but we can also go the other way. If we look at the left side, say, and there's a sine squared, and on the right side there isn't, but we have a 1, substituting sine squared plus cos squared for that 1 is likely to get us moving the right direction. Equally, going the other way on the left might get us where we need to go. Okay, so I'm just going to go over the ones that are in the textbook for now. You'll see lots of them over the course of the next few days. So simple, prove that sine of 2x is equal to 2 sine x cos x, and then illustrate by graphing. We won't usually be doing that, but again, just for your own sake, to be able to check things if you're not sure ever, you can always kind of make use of that. So again, just proper format here. I'm not going to assume this to be true. even though I know that in the end I'm hoping that I will show that it is true. So working with the left side specifically here, sine of 2x. This is a special case of our compound formula, so we can change it to sine x plus x. When we have two different angles here, we start off by doing something like this, where each one gets separated. Because the angles are the same, of course, they're just going to be straight x's. And then I have one sine x cos x here, and another over there. Left side equals right side. Okay. Now, how we're going to finish these up is quite important. Once we've got to this point, you got your left side equals your right side. You're all excited about the fact that, I'll leave that in there, that you got there. You have to be professional about it. You have to be mathematical. You have to sort of show this is what I know. And so at the end, we sort of finish it off with a proven. And you'll want to work on writing a really cool proven so that people recognize, hey, that was proven by Bob or Jane or Mary Ellen. So proven, so the PR, the O, the V, and then I get really cool at the end here. Squeeze that E and the N into each other and underline, boom, done. Okay, so moving forward, this is a compound formula, compound angle formula, sorry. The first angle is the pi over 2, the second is the x, and so clearly the more complicated of the two sides. Expand this out as we would with using the compound formula from before. And then sort of a key here, these two angles are not variables. These are actual numbers. Cos of pi over 2, cos of pi over, well, as you've seen recently, cos of something like pi over 3 has an actual value. So remembering what we saw before, this wasn't actually written anywhere before this, if we have an exact angle that we can simplify, go ahead and make that substitution. Now it turns out the cos of pi over 2, cos of 90 degrees is 0, and so of course we had 0 times cos x here. Sine of pi over 2 is 90, so 1 times sine x, and again, pretty easy. Proven. Now, cosines come into play, or cosecants come into play. Again, don't really like those, so we want to work with either the left side or the right side. Left side here, right side here. If we work with the right side, so let's just sort of see what happens. To me, it's not clear which one of these two might be the easier of the two. And so cosecant is 1 over sine, 2 over cos x down here. Now, with these, you want to treat this like a fraction divided by another value. So this is something that you'll start to do a fair bit. When I have a fraction over a fraction, or a rational over a rational, rewriting it with this division symbol is probably going to be quite helpful for me. And so this is 1 over sine x divided by 2 cos x, which is 1 over sine x times 1 over 2 cos x, which is 1 over 2 sine x cos x. So, to be honest, when I did this one, this is what I did to start. I wanted to actually come up with a solution here that was different than the one that that the book gave. Unfortunately, when I switched to the sort of at this point here, get a little bit hung up. I guess we could continue it based on what we saw back here. 2 sine x cos x is the same as sine of 2x. Okay, so I guess we can keep going then. This is unintentional, but this is the same as, now assuming I didn't remember having just proven that, this is 1 over sine x cos x, sine x cos x plus sine x cos x. which is the same form as our compound formula for sine, sine and addition, sorry. And so this is 1 over sine of 2x. And at that point, I sort of remember, oh yeah, what I started with was cos of 2x. And so assuming I haven't actually worked with the left side at all, I would probably then just kind of quickly go to the point where that is my solution. Now I've got left side equals right side. And again, proven. Now you can see, if I had chosen to work with the right side, might have got hung up at this point right here, because I happened to have done something recently that I recognized as being similar to that. I knew I could keep going with it, and I got to the point where I found a proof on that line. Obviously, another option would have been to go through working with the left side first, and as we expand it, oh, look at this, right here, there's another match to what's over here. So if I had stopped at this 2 sine x cos x point working with the right side, I would have found a match and been done on that line there. Again, textbook kept going though, and got to the point where here they found the exact original starting right side. So you want to understand that right there we've got at least 3 different solutions. If I had stopped at that point and then started on the other side, I would have got my proof completed right there, which probably was the nicest of the 3 options, probably the easiest of the options. Because I continued on, I sort of recognized that I could continue on. I was able to get a proof down here at the very bottom that matched up with the second line over here. Okay, so again, all of these would be complete solutions, whether it's the matchup here with the original, whether it's the matchup here with the second line, sorry, with the third line, or whether it's the matchup at the very bottom with the second line. Any combination of those is a perfect solution. So we'll hurry through the next one. I just wanted to make one comment about it because I don't think it was super clear. So left side, right side. The left side does look more complicated to me, so I would tend to start with it. Certainly, if there was something I can do on the right side, and I may come back and do something on the right side at some point as well. But what happens was we have the 2 compound formulas here, compound angle formulas. I keep saying that wrong. And so when we try to work this one out, we get cosine with the subtraction. This one, cosine with the addition. And then the line that's kind of missing here that might be missed by some of you, this is a difference of squares on this line. We have something minus something, the same thing plus the same thing. So the form of that is exactly the same as this, which when expanded is x squared minus y squared. Or again, going the other way, when factored, we get that. So what we have in here is this term times itself, so that term squared, cos x squared plus, or sorry, cos x squared, cos y squared. We then also have this term times itself again to get the second value here, or the second part of the expression here. What we missed in between, or what happens in between, is we have a cos x, cos y, cos x, cos y, times sine x, sine y, and we have a negative cos x, cos y, sine x sine y. So we get this times this gives us the positive, this times this gives us the negative, and of course, all of that just goes to 0. And so the middle term essentially disappears. And then as we continue on through, right here, when I kind of keeping an eye on the right-hand side, I see I'm getting terms down here that have signs in them. And up here in the right side that I'm trying to match with, I don't have any signs. And so, or sorry, sine squareds. I don't have sine at all, but I don't have sine squared specifically. So at this point, the thought is, well, if I can get rid of the sine squareds, then I'll be closer still to where I want to be. So sine squared is the same as 1 minus cos squared. That's the Pythagorean identity turned around or rearranged. And so if 1 is sine squared plus cos squared, well, 1 minus sine squared, 1 minus cos squared is the same as sine squared, whatever the angle happens to be. So we got 1 minus cos squared x, 1 minus cos squared y, and then it's a matter of basically multiplying it out, simplifying, and we see that we end up with a cos squared x, cos squared y, and a minus over here, and so we end up with the same thing on both sides. Please don't forget to practice writing your proven. Sorry.